Hello, everybody. I'm Reza Ahmadi, a PhD candidate from Dr. Yullah's lab at the University of Alberta in Canada. Today, I'm going to share with you some of the information about my project on the synthesis of bio-based freestanding nylon films from plant oil. So I'm going to kick off my presentation with a brief introduction on the polymers, their challenges, and the opportunities to tackle those challenges. I will talk about the material and methods for making two different kinds of bio-based polyamides called Biobased PA, DMOD-PXDA, and the Biobased PA, DMOD-PXDA. Then I also discuss some of the results from analyzing those polyamides, and then I'm going to wrap up my presentation with a brief conclusion. First, let's see what the polymers are. The polymers are macromolecules, which are created from joining together of small units called monomers. Nowadays, they are in each and everywhere of the human life. We can use them to protect ourselves, make house, electronic devices, paints, different parts of a car, beauty products, etc. So they are valuable products for making our modern life. But there is a big challenge regarding those valuable products. The production of the polymers is dependent on the fossil fuels, which have a limited range in nature, and their extraction and exploitation caused serious problems in nature too. But what would be the opportunities to avoid those problems? During the last decades, the renewable resources as a feedstock and the microwave technology as a heating source have been considered as the potential opportunities for the polymer industry to tackle those problems. That's why we conceptualized the synthesis and characterization of canola oil-based polyamides using microwave technology. For this purpose, canola oil was used to produce a bio-based chemical platform called dimethyl 9-octadecanoate or DMOD through the esterification of canola oil as the first step for separating the free fatty acids from the glycerol. The free fatty acids were then converted to a mixture of different chemical platforms, including DMOD, through an efficient microwave metathesis reaction in less than 1 minute and in a solvent-free media. Then the DMOD was purified from the rest of the chemical platforms using column chromatography. The semi-aromatic polyamides, DMOD-PXDA, was produced through the reaction between dimethyl 9-octadecanoate and an aromatic diamine called xylylene diamine through a stepwise heating process using TBD as a catalyst and in a solvent-free medium. Although the traditional polycondensation of monomers was completed after 3.5 hours reaction process at the final temperature of 205 degrees centigrade under vacuum, the microwave polycondensation of monomers was completed just after 15 minutes at the final temperature of 160 degrees centigrade under vacuum. Unfortunately, monomers couldn't tolerate more than 160 degrees centigrade under microwave irradiation. It could be potentially due to the decomposition of monomers under microwave irradiation at higher temperatures. The product of the reaction was concentrated in hexafluoroisopropanol, or HFIP, and then the polyamides was precipitated and washed using cold methanol. The product of the reaction was a white to yellow polyamide, like what you can see in this picture. To produce the linear polyamides DMOD-PXDA, dimethyl non-octadecene 8 was polycondensed a linear triamide called diethylene triamide through one-step heating process at 160 degrees centigrade under vacuum. Fortunately, the microwave polycondensation reduced the time of the reaction from 4 hours to less than 10 minutes. The product of the reaction was floated in water, and then the polyamides was washed with both water and cold methanol to produce this yellow to brown polyamide. According to the solubility issue of the polyamides, the carbon NMR spectroscopy was used to characterize the chemical structure of the polyamides. As you can see in the spectra of the polyamides, a peak at 174 ppm in the lowest field of the spectra is raised due to the presence of the carbonyl groups in the chain of the polyamides. In addition, a peak at 131 ppm of both polyamides spectrum is belonged to the unsaturated motif of the polyamides. A few more peaks in the range of 123 to 142 ppm of the semi-aromatic spectrum were attributed to the aromatic carbon atoms in the phenol rings of that polyamide. There are some peaks in the range of 18 to 46 ppm of the polyamide spectrum related to the aliphatic methylene carbon atoms in the chain of the polyamides. Another peak at 51 ppm of the semi-aromatic polyamides DMOD-PXDA related to the carbon sites between the phenol rings and the amide group of that polyamide. The thermal properties of the polyamides were investigated using different methods, including differential scanning calorimetric, thermogravimetric analysis, and dynamic mechanical analysis. As you can see in this table, the semi-aromatic polyamides are generally more thermally stable than the linear polyamides. All the polyamides had a melting point more than 145 degrees centigrade, except the traditional polycondensed linear polyamide with the first melting point of 45 degrees centigrade. Although the semi-aromatic polyamides started to decompose at a temperature as high as 355 degrees centigrade, the linear polyamides couldn't tolerate more than 124 degrees centigrade. Regarding the glass transition temperature of the polyamides, different heating methods had significant effects on the TG point of the semi-aromatic polyamides, while they didn't have almost any effect on the TG point of the linear polyamides. Therefore, the traditional polycondensed semi-aromatic polyamides had a TG point as high as 78 degrees centigrade, while the linear polycondensed, the microwave polycondensed semi-aromatic polyamides show a TG point around 40 degrees centigrade. And the linear polyamides had a TG point around 10 degrees centigrade. The crystalline structure of the semi-aromatic polyamides DMOD-PXDA was analyzed the wide-angle X-ray diffraction analysis. As you can see, the deconvoluted peak of the semi-aromatic polyamides produced under different heating process. Traditional polycondensation encouraged the polyamides with higher diversity in the crystalline phases, while the microwave irradiation produced polyamides having gamma phases but not the amorphous phases. The apparent degree of the polyamides crystallinity was calculated using this formula by dividing the area under the peak of the crystalline phases by the total area under the peak of both crystalline phases and the amorphous phases multiplied by 100. Fortunately, microwave irradiation promoted the crystallinity of the semi-aromatic polyamides to 100%, while the semi-aromatic polyamides treated under the traditional heating process had about 79% crystallinity. The VAX analysis of the linear polyamides DMOD-PXDA showed the polycondensation of them under different heating process also followed the same crystalline behavior. More diversity in the crystalline phases of the traditional polycondensed polyamides, but gamma phases with no amorphous phases created in the polyamides produced under microwave irradiation. Here, the microwave irradiation produced, again, polyamides with 100 crystallinity, while traditional polycondensed produced polyamides with about 90.3% crystallinity. The polyamides film were prepared using compression molding method. The polyamides needed to be molded under about 3000 psi pressure. The required time and temperature for molding the polyamides was about 20 minutes at about 160 degrees centigrade. Why? Except the traditional polycondensed polyamides, semi-aromatic polyamides DMOD-PXDA that needed to be heated at 200 degrees centigrade for about 25 minutes. The polyamide films were then annealed at 130 degrees centigrade for about 12 hours under vacuum. They were cooled down to their room temperature using stepwise cooling procedures. By reducing 30 degrees centigrade, by reducing the temperature 30 degrees centigrade in each step, and let the temperature remain stable in that temperature for about 3 hours. The mechanical properties of the polyamide films were investigated using a universal testing machine. As you can see in this picture, the semi-aromatic polyamides DMOD-PXDA show the characteristics of a brittle thermoplastic polymer, while the linear polyamide DMOD-DETA illustrated the characteristics of a rubbery and very flexible polymer. Regarding the semi-aromatic polyamides, DMOD-PXDA, different heating methods didn't have almost any effects, any significant effects on the tensile strengths of those polyamides, which was around 19 megapascal. However, the percent elongation at break of the traditional polycondensed semi-aromatic polyamides was almost 3 times more than the one produced under the microwave radiation. Regarding the linear polyamides DMOD-PXDA, traditional polycondensed linear polyamides had the higher tensile strength, while the microwave polycondensed linear polyamide had a higher percent elongation at range. In comparison with their counterparts. These differences could be due to the differences in the molecular weight, solid dispersity, and the crystalline structure of the polyamides produced under different heating methods. As a conclusion, we can say that the canola oil had a great potential to be used for making different chemical platforms for the polymer industry. Both heating method and type of amines has a significant effect on the properties of the polyamides, which are not soluble which are not soluble even in the strongest solvents for the polyamides like HFIP. Microwave irradiation can produce polyamides with higher crystalline structure, lower solid dispersity, as well as lower melting point. The semi-aromatic polyamides film were brittle thermoplastic polymer, while the linear polyamides DMOD-PXDA films showed the characteristics of a rubbery and very flexible polymer. Here, I should mention that the data of this project were recently published in the High Impact Factor Journal of ACS Sustainable Chemistry and Engineering. So if you would like to know more detailed information about this project, you can read the published data in that journal. Finally, I would like to say thank you to the Alberta Innovates and the Alberta Canola Producers Commissions for their time as the financial supports as a financial supporter of these projects. I would like also say thank you to Dr. Yula as my supervisor for providing the opportunity to be under his supervision. Last but not the least, I would like to say thanks to all of my lab fellows for their great support. Thank you for your attention.